Welcome back, everyone. It is time to tackle the FRQ portion of the exam review. So one thing I'll say about the FRQs is when I made this exam last year, this FRQ is not based on the current version of the exam. Because last year when I made this FRQ, I didn't know what the current version of the exam was. They changed the format of the AP Physics 1 exam last year, so that was year 1. We're now in year 2, I now have a better idea. So that's to say that the style of FRQ is not really going to look like this. One thing that we're going to talk about throughout the year is that the FRQ styles are pretty consistent in AP Physics, and we can use that to our advantage, but this breaks that style. This FRQ is there more just to test your physics understanding. So with that being said, let's get into it. A car is stopped at a traffic light. Oops, did not mean to do that. A car is stopped at a traffic light. The light turns green. At time t equals 0, the car starts moving and travels with a constant acceleration. At that instant, a truck is traveling at a constant speed, vt, alongside the car. Which of the front, or with the front of each vehicle at position x equals 0 as shown above. The truck passes the car, but the car later catches up to the truck in front of the house, such that at time td, the front of each vehicle is at the position x equals d. So, can we kind of see what's happening here? So the car is stopped, the truck zooms past the car, it's moving at a constant speed, but the car is going to accelerate and he's going to catch right back up to the truck, and then at this point right here, the car will overtake the truck. On the axes below, sketch and label graphs of velocity of the car and velocity of the truck as a function of time. Indicate any important velocities or time. So we know that at time td, they are both at the same position. So I'm going to make that my end. Let's say, let's call this td. They both start at, or the car is going to start at a velocity of 0, and the truck is going to have a velocity of vt. So let's say this is vt. Let's do the truck first. The truck is easy. The truck is just moving at a constant velocity. Its velocity is not changing. It is just going to go the same velocity until it reaches td. For the car is accelerating with a constant acceleration. So it should have a constant positive slope, since acceleration is the slope of the velocity versus time graph. One last thing, it should also end up, they both end up at the same position in front of the house. So that means the area under both curves should be the same, since position displacement is the area under curve of velocity. So the car is, if it starts 3 below, it should end up here. The car is going to look something like that. The area under both of these curves is the same, which means the displacement is the same. The two students are discussing how the speed of the car compares to the speed of the truck when both vehicles are in front of the house. Student 1 says the distance traveled by the car and the truck is the same, and the time is the same, so they must have the same speed. Student 2 says, I don't see how that can be. The car catches up to the truck, so the car has to be going faster. Which aspect of student 1 reasoning, if any, is correct? Support your answers in terms of relevant features of the graph. So, always do what the question says. It wants us to use our graph to support our answer, so we're going to do that. Student 1 says the distance traveled by the car and the truck is the same, and the time is the same, so they must have the same speed. Student 1 is correct in this part. They both travel the same distance in the same time. Both travel same distance in same time. it's hard to write, but also keep the camera steady, so the handwriting is not there, and I apologize. Both travel the same distance in the same time. And we can see that with the graph. The area under both curves is the same at time td. So let's also say that. Is same when at td. We don't have to explain what the student got wrong, just explain what the student got correct. So we can end it there. But the student is incorrect that they must have the same speed when they're in front of the house, because that's what this argument is about. They're comparing the speed of the car, the speed of the truck when the vehicles are in front of the house. That's not true. Student 2 gets that correct. I don't see how that can be. The car catches up to the truck, so the car has to be going faster. Student 2 is correct in that. The car has to be going faster when they are in front of the house. Car is going faster in front of house. And that can be seen on our graph just by this. The v of the car, and here's the v of the truck. The car's velocity is higher than that of the truck's velocity at td. So v car is greater than v truck at td. The average speeds, what student 1 may have been talking about, is the average speed. The average speed across the trip is the same, since they both took the same distance to get to the same time to go the same distance. But the instantaneous speed in front of the house, the car is going faster, because the car had to catch up to the truck. So when it ended, the car is moving faster. Derive an expression for the acceleration of the car. Express your answer in terms of d and vt, which is the velocity of the truck. So we need to find the acceleration of the car. Let's just start off with this one. Delta x equals v naught t plus 1/2 at squared. So always write the equation you're basing it off of, because sometimes what's the point? Did they do, like the scoring guidelines will literally say derivation that starts with this equation. So you get a point for just picking the right equation, and this is the right equation. It's got everything we need: acceleration, distance, velocity. We are going to have to edit it a little bit. So delta x is d. We're defining that as d. That is the distance that is being defined here. So the delta x is going from x equals 0 to x equals d. The car has no initial velocity, so this term goes away, and we're just left with 1/2 a t d squared. So the car travels d in a time of td. Let's substitute in td. And let's solve for a. A is equal to 2d over td squared. Now, this is not the answer, because we're not asked to solve for in terms of td. We're asked to solve in terms of vt. So let's look at the truck. Let's use this equation and adapt it to the truck now. The truck traveled the distance of d. The velocity of the truck is vt, and it did that in time td. The truck has no acceleration, so now this term goes away. Let's solve for td. td is equal to d over vt, and the reason we did that is so we can substitute back in td. So we're going to plug that in there, and we get a is equal to 2d over d vt squared. And we can box this answer if we want to, but I'm going to simplify a little bit more. So we have 2d over d squared over vt squared. That will cancel out with that. and then that will go up top. So it's 2vt squared over d. And that is our answer. That is the acceleration of the car. The tricky thing with this is just recognizing we had to solve for in terms of the velocity of the truck, not the velocity of the car. So we had to use two expressions, one for the car and one for the truck, and relate those two to each other. Determine the time at which the speed of the car is equal to the speed of the truck. Express your answers in terms of TD. Justify your answer. If we look back at our graph, when is the speeds of the car and the speed of the truck going to be equal? It's going to happen right here. And because it's constant acceleration, that has to happen right at 1/2 TD. Because in order for the areas to be equal, we need exactly as much area here as we do area here, so they cancel out. So that just needs to be halfway through. So 1/2 TD is our answer. And justify your answer. I'm just going to reference my graph again. It is when the two lines intersect. And that's honestly good enough for this one. Alright, that concludes the FRQ. Once again, if you have any questions, if you need me to go anything more detailed, don't be afraid to ask me in class. Otherwise, have a good day, everyone. Good luck on your exam. And I'm going to be signing off now. All right, bye.